All right. Let's wait for a few more minutes, a couple more minutes. Because people are a little slow in joining today, looks like. Yep. Guys have any questions so far about any logistical questions about the homework? Or I should mention something actually based on a discussion I had with Chelsea yesterday at the office hours. By the way, you guys know that I have office hours on Wednesdays, right? From 5 to 6. So not too many people seem to show up. So but I just want so make sure that you know that I do have office hours from 5 to 6 on Zoom. The Zoom link is on the website. The other thing I wanted to mention was that some of you asked me about the textbook. So if you don't have a copy of the textbook, there is a hard copy on reserve in the library, but that's probably not of that much use to you. But what I realized yesterday was that you can just go to the library website and then look at a soft copy on your computer screen. So just search for the textbook on library.illinois.edu, and you need to log in with your authenticate, and then it gives you access to a soft copy on the screen. You can't download it, but you can look at it on the screen. Okay. So in case you want to read material that I suggest some reading on each homework assignment. If you want to go read that up, those sections, you should be able to do that even if you don't have a hard copy of the book. Okay. All right. So any other questions? Anything about the last lecture on neural networks? Nothing? Everything was clear? Okay. All right. What about okay, so you'll have your new homework assignment probably later tonight, so homework 3, and it'll cover lectures 8 through 12 essentially, and then the exam will be based on the material for homeworks 1 to 3, so lectures 1 through 12. Okay, and the exam will be like about a week after, the Monday after homework 3 is due. So it'll be between homework 3 and homework 4. And next Monday is when, the 28th, is when you guys will have to demonstrate your code for the computer assignment to the TAs. Okay, so don't forget that. Oh, and at some point for the graduate students, maybe soon after the first midterm, I should say that the students taking it for 4 credits, I'll ask you to start forming groups of 3, teams of 3 students to work on your, on your project, on your paper project. And I'll give you some details on what I expect from that. Okay. All right. Any questions? You guys are awfully quiet today. Okay. Unmute and ask if you have any questions.
For the exam, how many lectures will it cover? Did you say? Can you say that again?
It's 1 through 12. So the first 3 homework assignments.
Okay, and will you be discussing a little bit in details about the question format for the exam later, or? I mean,
yeah, I can do that.
Okay, sure.
Okay. I haven't said it yet, so so when I said it, I'll give you some information on it. Probably the Thursday before the exam. Okay, so it's not much I'm going to review about neural networks. It's basically the idea was that you can use the structure of the neural network and let's see. Yeah, so we use the structure of the neural network and the chain rule to compute the gradient of the loss function that you're trying to minimize with respect to all the parameters. That's the weights W and the vectors B and the matrices W and the vectors B, all the components of those matrices. You compute the partial with respect to all the components, and you can do that efficiently by using the structure of the network. And then, so when you complete doing that, you have the gradient, and then you can apply gradient descent procedures to try and find the optimum values, the one that minimize the loss. Okay. All right. So that was that. So today's lecture is going to be about constrained optimization. Okay. All right. So what we have talked about so far was unconstrained optimization. And if you remember, we briefly at the end of lecture 2, we talked a little bit about, we had this picture that I showed, and I said, well, if you have a constraint like this, then you know, at the local minimum here, right, or a local max here, the gradient may not be 0. Okay, so if you remember in lecture 3, the following lecture, we actually found necessary conditions for optimality for unconstrained optimization. So if it's unconstrained, okay, then of course we showed that the gradient must be 0, okay, and then we also showed that we also had second order conditions, that the the Hessian must be positive definite for a minimum, and that condition, non-negative for a local minimum, and that condition, if you make it strict, so this was the second order condition, and then if it's strict, then it's you go the other way. It's also a sufficiency condition, right? So that was all for unconstrained optimization. So let's see what happens when you put a constraint, and let's start by assuming that the constraint is an arbitrary set S, but we'll put some conditions on the set first. And then we'll consider other things. Next week, we'll talk about other ways to do constraint optimization. But here, let's assume that S is a non-empty, closed, and convex subset of Rn. Okay. All right. So an example of that is in one dimension is shown here, and this is a closed, non-empty, and convex subset of R. Okay, and then I have this function here, and here if you have an interior point minimum, if you have a local minimum that's interior, the necessary condition for that to be a local minimum is that the gradient is 0. But if I look at extreme points, okay, then it's not clear. In this case, actually, these are both local minima, but what conditions do they satisfy? The gradient is not 0, so what conditions should they satisfy? So let's explore that, okay? And again, we're restricting ourselves to S that's closed and convex and non-empty. Any questions? Okay. All right. So let's actually first define what we mean by a local minimum when you have a constraint on X. So X star is a local minimum of F over the constraint set S if there exists some epsilon positive such that F of X star is less than F of X. I mean, that's a condition for even unconstrained local minimum, but this is actually, this just needs to hold for all X belonging to the constraint set, with X being close to X star. Okay. So basically, this definition of local min is the same as unconstrained, except that we put the condition that we only look at x's and s when we check whether x star, f at x star is smaller than f of x. Of course, a global min, if this inequality is a strict inequality for x not equal to x star. And then, okay. All right. So in an epsilon ball around x star. Okay. So now let's oh, no, this is, oh, shoot, no, this is not a global min, this is a strict local min. Okay, so let me fix that. I don't know what I was writing here. It's a strict local min. And what's a global min? What's a global min? Anyone? What is the definition of global min over SB? Someone. Yeah. Somebody unmute.
If the set is convex.
No, there's no well, we're assuming S is convex, but what would the global min? What would a global min over the set S be? All that has satisfied f of x star should be less than or equal to f of x, not just in the local neighborhood of x star, but for all x belonging to S. That would be the global min, right? A global min. It doesn't have to be unique, but that's. But a strict local min will have this inequality be strict for x not equal to x star. Okay. All right. So now let's see. This proposition here says that x star is a local min of f over S. Then a necessary condition for that is that not that the gradient at x star should be 0, but the gradient of f at x star dot product with x minus x star should be positive for all x belonging to S. And you can kind of see that in this picture. What is it saying is that if I look at the gradient, right? If I look at the gradient here, what's that gradient at that point, or the derivative at that point is what? Positive or negative?
Negative.
Negative. And so now if I look at any, so this is my x star here, and now if I look at any x, take the difference between x and x star, okay, and then and take the and multiply that by the derivative, I need to get something positive, because if I look at x minus x star, x is to the left of x star, so that's negative times the gradient is negative, and the product becomes positive. And here, the same thing. So here the gradient is positive. If I look at x minus x star, this difference, that difference is positive. The gradient is positive. The product is positive. Okay. So this idea is a generalization of that idea. This is saying that more generally, if x is n-dimensional, then the gradient of f of x star transpose or dot product x minus x star should be positive. Okay. Now, if f is convex, then this condition is also sufficient for x star to be a global minimum. Okay. All right. So, and think of an example of that would be something like this. If it's an endpoint, a minimum. So if I had a function like that, okay, then this would be, the condition here would be satisfied for this is a convex function, so then that gradient condition would be satisfied here, and it would be the global minimum of that function. Okay, let's see what else. Oh, I should actually show you a picture from the book. This result, of course, actually crucially depends on the set being on the S being convex, and there's a nice picture in the book to illustrate that. So this is a case where the constraint set is convex, and then you see that the gradient is here, and x is in this direction, okay, and the angle between x minus x star, the angle between these two is less than 90 degrees if this constraint set is convex, but if the constraint why is that didn't go? It's still showing the figure. Uh-oh. I see. Yeah, something is frozen, isn't it? Can you guys hear me?
Yes, now.
Yes.
Okay, now it seems to have fixed itself. Sorry. Okay, so let's prove this. Okay. It's the first time. Okay, can you guys hear me? Something happened again.
I can hear you now.
Yes.
I have no idea what's going on here. Okay. That is strange. There may be some issues with the internet at my home. Okay. Okay, so let me just show you what we did in lecture 3 for, you know, to get the necessary conditions for a local minimum. So we start off with this function g of alpha by defining this difference, and then we exploit the fact that if alpha is small, because x star is a local minimum, this will be positive, and that's what we use to establish that the gradient is 0. So if x star actually, even in our case, and we'll actually talk about this a little bit more later, but if x star is a local minimum here, and x star happened to be an interior point, not on the boundary, then we basically can go back and do what we did in lecture 3 and show that the gradient is actually equal to 0. That would be the same condition, necessary condition we had before. Okay, so the proof will only differ really because we are allowing x star to be also on the boundary. It doesn't have to be in the interior. So that's why you get a slightly different necessary condition to cover the case that x star could be on the boundary. Okay, is that clear? All right, so let's look at the same function, g of epsilon, which is f of x star plus epsilon x minus x star. Okay. Now the derivative of this thing, which we actually did this step several times before, is the gradient of this times, gradient transpose x minus x star. Right, the derivative with respect to x to epsilon. This was we did this step several times before, starting from lecture 2, I guess, or lecture 3. Okay, so and then we can apply the mean value theorem. This is again just a function of one dimension, r to r, it's g function. So this is g0 plus g prime of 0, but I want it to be an exact result. So I'll take g prime of, say, some beta times epsilon, okay, for some beta between 0 and 1. So this is the mean value version of Taylor's first order approximation. It's also called mean value theorem, the basic mean value theorem. And so now we can plug this in, and so we get that g of epsilon is f of x star plus epsilon x minus x star. So it's some deviation from x star, basically, that I'm looking at. So that's equal to f of x star, which is when epsilon is equal to 0, g of 0 is just f of x star, plus epsilon times, I'll plug in the derivative here, f of x star plus epsilon beta x minus x star transpose x minus x star for some beta in the interval 0, 1. Okay. Now, so we're going to assume that we assume that f is continuously differentiable. So the gradient is continuous. So for all epsilon sufficiently small, if I look at the gradient of f at x star plus epsilon beta x minus x star, okay, and transpose x minus x star. Well, we know that if I just had the x star there, if I just had x star here, it's negative, but by continuity, if I perturb that by a little bit, for epsilon sufficiently small, this perturbation is small, so by continuity, this will still remain negative. Okay. And so for epsilon sufficiently small, if this guy is negative, then I have that this is less than this. So f of x star plus strictly less than f of x star, because it's strictly negative. Okay. So, but now what do I have here? I'm going to get a contradiction, because if I look at this thing, actually we've seen this kind of combination before, x star plus epsilon x minus x star, I can rewrite it in a form that looks more familiar to you. So this is like 1 minus epsilon x star plus epsilon x, right? But this is just a convex combination of x star and x, but both x star and x belong to my convex set S. So now I'm exploiting convexity. So this convex combination belongs to anyone? Where does it sit? X star and x both belong to S, so the convex combination also must belong to S because S is convex. Okay, but then I've now found a point that's sitting in S that has a smaller value than the function of x star. So x star cannot be a local minimum. And that's a contradiction because we assume that to start with that we're trying to find a necessary condition for x star being a local minimum. So we assume x star is a local minimum, and then we assume that this condition held, so the opposite must actually hold because of the contradiction. Okay, so that's how we prove part A. Any questions?
Can you talk again why epsilon smaller than 0, we can have the term smaller than 0?
Oh, that's just by the continuity. So by the continuity, by the continuity of this gradient function, right? So if this gradient product is negative, okay, I mean the gradient is continuous. X minus x star is continuous. The product of these functions, the inner product of these functions is continuous. So I have a function that's continuous, that's negative. I perturb this by a little bit. It's not going to. It's still going to remain as long as I make my perturbation small enough. Okay, it'll still be negative by continuity. It can't jump somewhere far away, right? So something that's negative, if I perturb the argument a little bit, it'll still remain negative. If you want to prove it formally, just use the definition of continuity, which says that this guy, the perturbed value minus this guy, the absolute difference of that can be made less than some epsilon prime, as long as or made less than delta, say, as long as x minus as long as this this minus x star is less than something. And so as long as epsilon is small, then this difference can be made less than any delta that you like. And so the perturbed value minus this guy must be less than delta. So then if this guy is negative, then the perturbed value can be also made negative, because you can make your delta small enough so that that perturbed value is also negative. So you actually use this idea also in the first problem of homework 3 to show that a set is open. Okay, so it's just a definition of continuity. Okay, but intuitively, basically, if a function is continuous, it can't jump by a large amount close to the value at which you're evaluating a function. So if that value is negative, then close to that value, it should still be negative. Okay, and yeah, and you should be able to prove this on your own, mathematically, formally. I'm not going to do that. In fact, I'm going to test you on that in homework 3 for the first question in homework 3. So this should be something you should be comfortable with. If not, go and look at your undergraduate course where you learned these kinds of things, learn continuity. Okay. All right. So, but anyway, it's good that you asked that question, because you guys need to be comfortable with these kinds of ideas. Now let's see what happens with convexity. So if F is convex over S, right, then we have this condition that Fx is lower bounded by the Taylor series, first order Taylor series expansion, right, of x around x star, f of x around x star. So it's this. So this condition holds for all x belonging to S. We showed this in maybe lecture 3, right? And we used it a lot when we were looking at gradient descent. Okay, so now we know that from part A that this condition holds. This condition holds. This is now negative. So this guy is now negative, which implies that f of x is bigger than or equal to f star for all x belonging to S. So this is the condition for a global minimum. Okay. All right, so that proves the second part of the theorem. It says that if F is convex, then X star is also a sufficient condition for X star to be, then not X star, then this condition is sufficient for X star to be a global minimum. Okay. Any questions? With this correct definition of global minimum, by the way, not the one I wrote in your free notes. I don't know what I was thinking here. Yeah, this is the correct definition. All right. All right, here's another interesting fact. And suppose X was an interior point, and we mentioned this again. If X is an interior point, then whatever we did in lecture 3 goes through unchanged. Necessary condition, all the stuff that we derived, in fact, even second order necessary condition, all that stuff goes through if X is an interior point, X star is an interior point. So we don't have to do anything different. You just get that the gradient is 0. If X star is local minimum, the gradient is 0 at X star. Right. So the only reason, and it doesn't contradict the result that we just proved, because that's definitely a possibility, right? If the gradient is 0, then this product is going to be 0, which is non-negative. It doesn't contradict the result. So if X star is an interior point, you get back the previous result. Okay, also if F is convex, we show that the gradient being 0 is a sufficient condition for X star to be a global minimum. Okay. All right. So everyone happy with that? Okay, so now we're going to say a little bit about how we can try and develop a gradient descent procedure that works when you have a constraint. So all what we've talked about, all the gradient descent stuff that we discussed before really applied to unconstrained optimization, right? We didn't put any constraints. So when we talked about Army-Hose rule and fixed step size and so on, or even when we talk about Newton's method, we were really talking about unconstrained optimization. Okay, so let's in order to get there, we need a concept called the projection theorem, or a result called the projection theorem, or the concept of a projection. Something you may have studied in the previous course. Okay, so here so if S is a closed convex subset of Rn, which is what we have, okay, for our constraint optimization, then we say that for any Z, doesn't have to belong to S, can be outside of S. The projection of Z onto S is denoted by, and this slightly different notation than your textbook. This textbook uses a Z plus here, and I don't like the plus because I'd like to see the convex set being mentioned in the projection. So I put a superscript of this set S on Z. So Z superscript S like this, or Z bracket superscript S, is the projection of Z onto the set S. Okay. So pictorially, and we'll draw another picture a little bit later, you have a set S, closed convex set S, and you have a Z, say, that's sitting out here, and basically there's some point inside the set S. I'll call that the projection. And what does this point have to satisfy? It's a point that minimizes the distance to that set. So minimum for y belong to S, the squared norm difference. Okay. So it minimizes the L2 distance of Z from the set S. Okay, so that's the definition of a projection. That's this point here that is the smallest, it's one that has the smallest distance among all these points to this point Z. All right. Everyone happy with the definition of projection? Okay, so now we'll give a result about projections. Okay, this is the projection theorem. So for every Z, the projection is actually unique. So there's a unique projection. And now we're going to, and the second part of the theorem says that there's a necessary and sufficient condition for something to be a projection. Okay, so that this will help us identify a projection. So a necessary sufficient condition for something to be a projection, say y star is the value of y that is basically the one that's the closest in distance to Z in the set S, if and only if this condition is satisfied. If I look at y star minus Z transpose and y minus y star, this has to be positive for all y belonging to S. Okay, so we're going to prove that in just a minute. And the third part of the projection theorem says that the projection is non-expansive. So if I look at the distance between the projected values of two points, X and Y, okay, this is less than, or maybe I should call that Z, just to be Y I'm using as the variable for my set, so let's call that Z. And so this is less than or equal to X minus Z for all X, Z belonging to Rn. Okay. And pictorially, maybe I should show you the picture that's on the next page. Hold on. This is the picture. Basically, if I have the set S, okay, I have 2 points X and Z. I project X onto the set S, project Z onto the set S. If I look at the distance between the projected values, there's always going to be smaller than the original distance between X and Z. Pictorially, it kind of makes sense, right? Because S is convex. Right? We actually prove this mathematically now. Okay. All right. Okay. First of all, first let's look at the uniqueness, right? So there's a unique projection. So, okay. So first, can we apply? I'm trying to first, does the minimum exist for this function? First of all, the minimum exists. So if I look at this is a quadratic in y, right? Z minus y whole squared, and a quadratic function in y. Okay, if I look at the minimum over all of Rn, and what is that? If I didn't put the constraint S here, what would the minimum be?
0 when y is Z.
The minimum value is 0, but when y equals Z, that's correct. So that's the minimizer would just be y equals Z if I didn't put any constraints, right? And we know that it's a quadratic function, it's a coercive function, it must have a minimum, and it's actually strictly convex. So it's a unique minimum. So we know that the minimum will be unique if I didn't put any constraint. So what happens if I do put a constraint? Then I have to worry about whether there's first of all whether there's a minimum, and whether it's the second question is whether it's unique. So in order to prove that, what we go through a slight step here, and this you can think of as a slight modification to the corollary to Weierstrass's theorem. Okay, so let's see what that is. Okay, so what we do now is, because now that this function z minus y squared is basically unbounded, and all we assumed about the set S was that it was closed and convex. We didn't say anything about it being compact. It may not be compact, right? So if it's not compact, then we can't apply Weierstrass's theorem directly. So what we do instead is basically we exploit the nature of the function, the fact that it's a quadratic, and it actually blows up as y goes to infinity. So it's actually a coercive function in Rn, but it's not going to necessarily blow up on the set S, right? Okay. So what we do is we minimize, we fix an element x belonging to S. Okay. Now we are trying to minimize this quantity over all y belonging to S. So minimizing z minus y squared over the set over the following set A, which I'm going to define now, is the set of all y belonging to S such that z minus y squared is less than z minus x squared. So I'm basically fixing one point. It's not necessarily the minimum, and looking at all the points y such that for the z minus y squared is less than the z minus x for that fixed point. Now clearly, minimizing this is equivalent to minimizing z over all S, right? Right? Because I don't care about values that are larger than z minus x squared anyway. I'm looking for some things that are smaller. So these two are equivalent minimizations. But the nice thing about this set, this is basically saying this is a quadratic being less than some constant. So this is like a sphere in n dimensions. It's the interior of the sphere and the boundary. So it's actually a compact set. Okay. So now we are trying to minimize a quadratic function, which is a strictly convex function. So even though S may not be compact, minimizing over S is equivalent to minimizing over this A, which is a compact set. So, and G is strictly convex, and we are minimizing it over a set A, which is compact. So by Weierstrass's theorem, the minimum exists, and by the strict convexity, the minimum is unique. Okay. Is that clear, the argument? Okay. All right, let's move on. So that was just the first part. So now let's look at the second one, which is, if there's a y star, by the way, the y star has to be unique, then a necessary sufficient condition for it being the projection is that this condition holds. So let's prove that. So to prove that, we actually use the necessary we'll use the condition we just established for a necessary and sufficient condition for convex functions in the previous result. So let's just remind ourselves of that result first, and then we'll come back to this. Okay? So what is the result for convex functions? A necessary and sufficient condition for a convex function for x star to be a global minimum is that this thing holds, right? The gradient times x minus x star should be positive for all x belong to S. So we can use this now because the function we're trying to minimize for the projection is a convex function. It's strictly convex function, actually. So it's a unique global minimum, we know that. Okay, but but in order to apply that condition, we need the gradient of that function, right? So this is strictly convex. Write that down. And so we need the gradient. The gradient of this function is easy to compute. It's just 2y minus. Okay. So for from the optimality condition, which necessarily sufficient condition for y to be a unique minimizer of G over S is that the gradient of G at that y star should times y minus y star should be positive for all y belonging to S. But then I substitute for the gradient there. This is saying that y minus y star minus z transpose y minus y star is non-negative for all y belonging to S. Okay, which is exactly what we wanted to prove. Right? Y minus z transpose y minus y star is non-negative. Sorry, did I write that correctly there? Yeah. Y star minus z transpose y minus y star is non-negative. That's what we put. Y star minus z transpose y minus y star is non-negative for all y belonging to S. Okay. So now let's prove the non-expansive property, and we'll use B, the result of B, to do that. So we'll actually apply it in two different ways. We'll apply it to both the x and the y. So for the non-expansive property, we want to show that if I have 2 points, x and z, and project them, then the distance between these guys is smaller than the original distance. So let's the projection of x is x sup s, and z is z sup s. Okay. So let's apply the result from B to both of those projections. So we know that x, the first result is that x sup s minus x transpose y minus x, x sup s is positive. And then the same thing to z sup s minus z transpose z sup s is positive, or non-negative, sorry. Okay. Now what I'm going to do is in the first inequality, in 1, I'm going to substitute y equals z. I could put anything, any y belonging to S. I know that the projection of z on S belongs to S, so let me plug that in 1. And I'll plug in y equals x sup s in 2. Okay, so this here basically I'll plug in z sup s, and here I'll plug in x sup s. Okay, so basically these two quantities are the negative of each other. So if I add these two inequalities, what I get is z sup s minus x transpose this difference minus this difference. Right? So the first inequality gives me x sup s minus x, and the second one will give me z minus z sup s, and this inner product must be non-negative for all y belonging to S. Let's simplify that. What that says is that this difference is bigger than if we look at this difference, so one of these guys, Z minus X transpose Z minus X, is bigger than Z minus X transpose Z minus ZS minus XS. So on the right hand side of this inequality, if I take this guy times this to the right hand side, I just get the norm squared of the difference between Z and ZS and XS. Right? Are we going to see that? Any questions? Don't hesitate to ask. Okay, so now, okay, this is similar to what just a problem that you solved in homework 2. Whenever you see an inner product, okay, you think about Cauchy-Schwarz inequality, right? And if we look at Cauchy-Schwarz inequality, it says that this inner product is less than the norm, the product of the norms of these two quantities, and that basically gives us the result. So this says that we rewrite this. It says ZS minus XS norm squared is less than, by Cauchy-Schwarz, the norm of ZS minus XS times the norm of Z minus X. And one of these will cancel with this, and you end up with the norm difference between Z sup S and X sup S is less than the norm difference of Z and X. And so we prove that the projection is non-expansive. Okay, any questions? Sounds good. All right, so let's take a short break, and then we'll talk about how we apply the idea of projection to come up with a gradient descent type algorithm for constraint optimization. Okay.
Just to check, so in here when we talk about constraint optimization, is that like we consider the convex case first, and then later we'll touch on like non-convex, like this?
Absolutely, that's right. So we're first looking at closed and convex sets, right? For which we at least we have a hope that these minima will be achieved, and that we could find some conditions for the achievement. And then we'll talk about examples where special cases, I should say, and the special cases are going to be generated using inequalities. So inequalities or equality constraints, and so we'll talk about that from next week on, actually. So this discussion is restricted to convex, closed convex sets S.
I see. Thanks.
Right. If there are no other questions, let's take a short break, and then after, so it was 11:53 on my clock, so 11:55, we'll come back and then spend the last 25 minutes talking about how we apply this. All right. So any other questions? Or can we move on to what's called the gradient projection method for gradient descent? Okay. So again, we're going to assume here that the function is convex and S is closed and convex. Okay. And then we're going to figure out a way to find the minimum of the function over that set, convex set S. All right. So we could call this the gradient projection method, because what we're going to do is, by the way, this applies to either fixed step size, or you can also do it with variable step size, say this with step size chosen using army host rule. But let's talk about the fixed step size case, special case only here. Okay. So what we're going to do is we look at xk, just like what you do with fixed step size gradient descent. So you at time k, you have xk, which actually belongs to the set S, right? We're going to assume that xk belongs to the set S. And then at time k plus 1, you take a gradient step using that at that xk with step size alpha. But when you do that, and this alpha is positive, of course, when you do that gradient step, you may end up going outside of the set S, right? There's no reason for you to stay in the set S. So especially if xk was in the boundary, so I have a convex set S here, xk was in the boundary here, close to the boundary, and I take a gradient step, I might end up going out of that, and xk plus 1 goes outside. If xk plus 1 goes outside, what I'm basically going to do is force xk plus 1 to get back into S by taking the projection. Okay, so that's called the gradient projection method. Is that clear? Okay, so the algorithm in this in gradient projection terminates, we'll first establish that it must terminate at a minimum of f, assuming again that f is convex. In other words, we're going to assume that x star when it terminates and I do a projection, okay, I basically remain at x star. Okay, if x star is the minimum of f. So this is what we're going to do. So we're going to say that if this condition holds, okay, then x star must be a minimum of . So when you project and you don't change the original value, so you started off, so think of this as xk, and I'm trying to find my next xk plus 1, but it doesn't change. Then x star must be a minimum of f over s. Okay, so let's see why that's true. Okay, so x star minimizes f over s. F is convex, so we know from our necessary and sufficient condition for optimality that the gradient of f at x star transpose x minus x star must be non-negative for all x belonging to S. right? So now I'm just going to take alpha and pre-multiply this quantity by alpha. So I'll look at minus alpha times this quantity. But because I put a minus sign and alpha is positive, so this will become negative for all x belonging to S. Now I'm going to do massage this quantity a little bit. I'm going to take this minus alpha and put an x star and a minus x star with it. I'll take x star minus alpha minus, oh, sorry, no, I do it to the whole thing, to the whole quantity. Sorry, I need to do it to the whole quantity. That's not going to be enough to do. So I'll put x star minus alpha gradient of x star, and then I'll subtract out the x star to make things the same. So basically, this will cancel out, so that I've not changed anything. And then I take the transpose of that x minus x star as negative for all x belong to S. But if I think about this, this is the necessary and sufficient condition for x star minus alpha to be the projection of x star onto S. Okay, so let's see why that's true. I'm looking, so x star plays the role of Z in this, so think of x star as being Z. Okay, or maybe I should use a different color just to less confusion. Think of x star as Z, and this is basically my y star from the previous projection theorem. This is Z, and this is like my y in the projection theorem. So y star minus Z into y y minus Z should be negative, right, from the projection theorem. Yeah, so the projection theorem, if I have y star here, y star minus Z, so y star minus Z transpose y minus y star is positive, but if I had y star minus y here, that would be negative, right? Okay, so basically this is this result says that this guy is the projection of x star, or I should really say x star minus alpha. Oh, sorry, yeah, so this is my Z. Yeah, it's the other way around, sorry. Think of this as the Z, x star as the y star. So it's a little confusing, so sorry about that. X star is y star. Okay, and this is basically, this is my Z. Okay, so let's make sure that that's exactly what we had in the projection theorem. So let's go back to the projection theorem. So y minus Z transpose y star minus y is negative. Y minus Z, y star minus y. Y minus Z transpose y star minus y is negative. Okay, so this is like y minus y star. This is Z minus y star. So that product is also going to be negative. Okay, so what this says is that if I look at this quantity, this is my Z, its projection onto S is x star. That's what this result says. Okay, So let's actually change back to our other color. Erase all these things in green. So by the projection theorem, x star minus alpha gradient, this guy projected onto the set S is equal to x star. Right? So if x star minimizes f over S, then when I terminate, basically I'm at x star. Terminate meaning that my gradient basically doesn't change my iterate. My gradient descent doesn't change my iterate after projection. Okay. So let's so we have this result, and actually we can use this result to say something about the convergence of this gradient projection method, where at each iteration we make sure that we project back into the set S. Okay, and we make the usual assumptions that we made before for looking at convergence rates, which is we assume that it's Lipschitz gradients and strong convexity. Again, this is all restricted to the set S. Let's see what happens then. So we're going to exploit some of the properties of projection that we just proved. Right. So as usual, what we need to do is look at what happens. Look at so suppose xk, my kth iterate was close to x star by a certain amount. How is that related to how xk plus 1 is close to x star? So we just use the relationship that xk plus 1 is formed by doing the gradient descent step and projection. So that's what we have here. So if we look at the difference between xk plus 1 and x star, that's the same as xk minus this gradient projected minus x star. So now I can use this previous result to say that x star is the same as the projection of x star minus alpha times gradient f at x star. So I can replace x star by x star minus alpha times the gradient of f at x star from the previous result, projected. Okay, so basically I've replaced this x star by this from the previous result. But now I have the difference between two projected values, and we know by the non-expansive property of projection. So this is the previous result, and then this is the non-expansive property. What I can do is I can replace the difference between the projected values. I can upper bound that by just the difference between the values. Now I'm squared because I'm taking the square on the left-hand side. Okay, so now I can expand this out. So I can write this as just do the quadratic expansion. So xk minus x star squared plus alpha squared, the gradient of xk minus. Okay. And then I have the cross term minus 2 alpha xk minus x star transpose gradient of f of xk minus gradient of f of x star. Okay. So now I'll use the Lipschitz property. Lipschitz like we did before. This guy is Lipschitz, so I can upper bound it by, we call it L or M? Yeah, M, capital M, right? Use capital M for the, so this is bounded by capital M times the xk minus x star. So I can write this difference as xk minus x star squared 1 plus alpha squared m squared. And then I'll have a, I'll make the sign positive 2 alpha x star minus xk gradient of f of xk, and then plus 2 alpha x star minus, not x star minus x star there. Ugh, too much of a hurry there. X star minus xk gradient of f at x star. And then what I'm going to do is just add and subtract some quantity that I'll use in just a minute. Okay, I'm not going to change anything by doing this. Now I exploit the convexity of f to say that f of x star is lower bounded by f, it's a first order Taylor expansion around xk. Okay. And so now we have this is less than xk minus x star squared 1 plus alpha squared m squared, plus I can replace the first inequality, this guy here, I can replace that by 2 alpha fx squared, and fx star. And then what I'm left with is 2 alpha x, let's change the sign. Oh, sorry. So this one was wrong. The sign is negative on that. So this should be xk minus x star. Because up here, this and this have different signs. So yeah, this will be xk minus x star with associated with f of x star. Okay. And so I have 2 alpha. I need that actually, because the other way I can't apply my strong convexity result. To alpha f of xk, second line from there. Now apply strong convexity. So strong convexity says f of xk is bigger than f of x star plus this gradient plus half m times this quadratic. So you can conclude then that so this part I have two. So I have 2 alpha f of x star, so 2 alpha there, and then 2 alpha associated with this, and then the minus f of xk from this side. So I can replace all of that by half little m xk minus x star squared. So I'll just get that all that stuff just gets replaced by half with the minus sign m alpha. So I'll get xk minus x star squared 1 plus alpha squared m squared minus alpha m. And does that look familiar? It's exactly the same result that we had for unconstrained gradient descent, this step. So from this step, you can conclude that you have linear convergence. Okay. If you want me to remind you of that step, since we have a couple minutes, let's just go back to, let's see, which lecture did we do this? Lecture Was it lecture 7? Let's look at lecture. I think it was lecture 7. Yeah, so almost at the right point here, but it's exactly the same result that we had for the unconstrained case. So from here on, you can follow the same steps and then optimize your alpha and so on and so forth, and then you conclude. You come up with this result here, right? Which is the linear convergence result. Okay. So the gradient projection also has linear convergence as long as alpha satisfies certain conditions. So if you choose your alpha to be alpha star, you get linear convergence. Okay, but one remark here. So why would you not use this, right? So you basically get back everything you would have as regular gradient descent. So constraining this x to belongs to S doesn't seem to really make that much of a difference, right? As long as you do this projection. Okay, but what is the disadvantage? This projection step in general can be quite expensive computationally. So in order to make this projection, gradient projection method practical, the projection operation needs to be easy to implement. Okay, there are special cases where that's true. Okay, one of those special cases is when the constraint set is basically a box or a rectangular constraint set. So this says that each of the xi's is restricted to this interval between AI and BI. Okay, so in 2 dimensions, it would be a rectangular constraint like this. Or I should probably use my special magic feature to draw a rectangle here. Right, so that would be the rectangular constraint in 2 dimensions. And so basically, for the rectangular constraint, if I have an x that lies outside the set, to project onto the set, I just basically look at make the along the horizontal axis, I shouldn't call it x-axis, along the horizontal axis, I just make the value equal to the A1. I guess this would be A1, corresponding to A1. And then on the other side, I have B1, right? So if I'm to the right here to project, I'll make that value equal to B1. And similarly, if I'm coming from the top, I'll just make that value equal B2, and then this one will be A2. Okay, so it's easy to do the projection in this case. Okay, again, you can see that geometrically this is true. It's very easy to prove also mathematically that that's exactly what the projection is going to be. So what basically to project onto this set S, ZIS is just AI if XI is less than AI, BI if XI is bigger than BI, and it's just the same, unchanged if ZI if otherwise. Okay, so look at each coordinate essentially and see if it's less than AI or bigger than BI, and then you basically project onto those values in that case, and in between it's unchanged. So if it's in between, it's basically unchanged, right? Or maybe even here, if it's here, then you don't change the vertical axis, you only change the horizontal axis and make this equal to B1. Okay. Now, more generally, if the constraint set is a so-called polyhedron, which is basically a convex region that's bounded by hyperplanes, and in 2 dimensions, it's basically bounded by a set of lines that looks like this, then there are efficient ways to implement the projection. Actually, I shouldn't say that. There's efficient ways to do constraint optimization, okay? Not necessarily through projection. And there's a discussion of that in 3.4 through 3.6 of your textbook, if you're interested in looking at that. Okay. In your homework, you'll also see that it's relatively easy to project onto sets of this form with linear constraints of this form. So if my constraint set S is the set of all x's such that AX is equal to B for A being some M by N matrix with full rank. Okay, so rank equal to N. So A is M by N and A transpose is invertible, right? Is non-singular. So in this case, actually, there's a nice formula. You can actually explicitly write down the projection onto the set S. And you know, I'd like you to, I give you the answer and I ask you to verify that it is the projection in your next homework. Okay, but in general, this projection operation can be quite expensive computationally, because basically what you're trying to do is you're going to solve another optimization problem to find the projection, right? You have to solve this optimization problem. It's convex at least, but still, it's an optimization problem that needs to be solved separately in each iteration of your gradient descent. So that could be expensive, unless you have an explicit formula for the projection. Okay. So what we're going to talk about next week, I'm going to give you a little preview. We're going to look at when the constraint set is defined by inequalities. Okay. And in that case, inequalities are equalities. And in that case, it turns out that one can develop a separate theory for that kind of constraint optimization based on what's called Lagrange multipliers. Okay. And for the next few weeks, we'll be talking about that. We're going to be talking about those kinds of constraints and how you do optimization of those constraints. Okay, so we will not spend that much time on the more this problem of optimization over a convex set and using things like gradient projection to solve them. Because there's a much richer theory when the constraints are defined by equalities or inequalities. And also in practice, it turns out that those kinds of constraints are quite prevalent. And so that approach turns out to be a lot more useful in practice. Okay. Any questions? Oh, we have run out of time. Okay, so if you have any burning questions, ask. Otherwise, I'll see you guys next week and have a good weekend.
I have a question. It was about the last page.
Yeah.
One of the inequalities in the proof.
This one?
Yeah, in the proof. No, I should just pull it up. It was when we were. It was before we used the optimality condition.
This one? To prove that it's this projected onto S is X star?
No, it was the to prove convergence.
Okay.
Okay, here
This one?
is the gradient projection method.
Yeah, this is the gradient projection method.
Okay.
So,
We
so
said by convexity, starts with biconvexity.
Oh yeah, this is convexity. This is where we're exploiting convexity.
I don't think your screen is updating. It's showing the projection theorem.
Oh shoot. Yeah, I don't know what's going on.
That's okay. I'll look at it again.
I was talking about things on my screen, but it's not showing anything different up there, is it? I'm not sure what's going on. Sorry. So
That's okay.
maybe
I can put it off.
we can talk about it in the office hours. Okay.
All right.
All right. Okay, see you guys next week.
See you.